Okay, thanks everybody. So our speaker today is really grateful that gave a talk on Sunday evening. So I think that's something we want to think about going forward, is whether for the North Americans we shift so it's not Sunday night for those who want to join us. But Gene's talk is quite an interesting one that's sort of looking at how we can link, as I understand, process-based models to geological kind of processes, which is something I was always quite intrigued about whether that could be done. So Gene is based at Kansas, University of Kansas, where he's a professor there, and his work focuses on looking at some of the drivers of Earth surface processes, geomorphology, and links some of the issues between geology and Earth surface processes. And a lot of this work, I understand, is focused primarily on tropical systems, which I know there's a lot of people attending today that are very interested in those kind of questions. So Gene, as you would have seen, his title is Testing Geological Concepts Using Numerical Hydrodynamic Process Models. So I'll turn it over to Gene now, who sharing should be fine, I think.
Okay, thank you, Ryan. Thanks for the invitation. Thank you, everybody, for attending. Let's see if I can manage to share my screen now. Okay, is that all right?
Yeah, perfect.
Beautiful. Well, again, thanks everybody for attending. I appreciate the invitation, and it's an honor and a pleasure to be here to chat with you all and hopefully get some discussion and feedback as well. So we're going to talk a lot about numerical models, but I want to start with conceptual models. And geologists love conceptual models, and figures of conceptual models from the magnus opus of many sedimentologic and stratigraphic papers, and mine included. And conceptual models are important for a number of reasons. First of all, they're essential for organizing observations and data collection, for analysis of those observations, for interpretation, and finally, and most importantly perhaps, for prediction. But some conceptual models, well, they kind of really just leave you scratching your head. I'll just put a few examples up here. First is, here's one. Here's sea swell energy coming in, a nice calm sailboat, hit some sort of a bump here, and then all of a sudden we get storm wave base develop behind that bump. So I just kind of scratch your head a little bit on that one. Here's another one where the author invokes shore parallel ooid bars, continuous ooid bars. There's a number of these things which are all lined parallel to the shoreline over here. And that's not really resembling anything we see in the modern today, in ooid shoals today. And here's another one for those of you who are more hydrodynamically inclined. See the wave crests go over barrier islands with basically minimal diffraction or distortion or disruption. They just continue all the way across there. So some of these things, well, they're at least plausible, but they make you go, At least they make me go, Okay, that's enough of that. So I have a few take-home messages. First of all, sedimentologists and stratigraphers, myself included, are quite creative. Second of all, conceptual models can and really should be tested numerically, and that's kind of the case that I'll make here. And in doing so, hopefully I'll show you two scintillating studies that will show us that, number one, reef sand aprons will not, with an asterisk there, will not fill lagoons. That's kind of the first part of my talk. The second part of the presentation is on the wily basis of wave bases. So with that, let's go ahead and get started. And the first kind of maybe paradigm that we'll take a look at would be one that had been advocated before. A lot of folks in the Great Barrier Reef actually proposed something like this. But folks noticed that reef sand aprons grew towards a platform interior. And Ed Purdy and Abraham Geisler in 2005 published a paper where they basically looked at satellite images, and they said, well, in some cases you see reef sand aprons that are discontinuous or present near the margin. Other cases they extend a little bit further into the lagoon, and then finally some lagoons are almost entirely filled. And they said, well, this shows us that reef debris will fill atoll lagoons given sufficient time in the absence of sea level change and stuff like that. So, and it's certainly plausible, and it's an interesting concept, but is it physically realistic? Is it consistent with the laws of physics? So why do we care about this? Well, first of all, who doesn't love atolls? I know a lot of people here love atolls, as do I. So that's, of course, number one reason why it's important. Second of all, it's also important for the geologists. And there are a number of geological examples. I'll show you one here of the Devonian Redwater buildup from the Western Canadian Basin, where you see there's basically a marginal reef around the exterior. And then this yellow thing is what they call outer lagoon, which is basically coarse reef-derived debris. And these are important because this, in the past, has served as a hydrocarbon reservoir, but today it's actually being repurposed as a carbon capture and storage unit. So understanding subsurface heterogeneity. So these injection sites, the highest porosity and permeability, are present in the coarse-grained reef and reef sand apron deposits. So we need to try and understand what controls their distribution and their dimensions. So to do that, again, we'll take a look at some overly simplistic process models. We'll start with an idealized model. This is a model that's inspired, hang on, so I have to, there we go. These are models of an isolated platform like that one. It's inspired by reality, but it's not modeling a specific atoll. So in this case, you can see here's a reef sand apron, then a lagoon. So we'll look at kind of a conceptual cross-section across this. Here's our digital representation of that real atoll from the South China Sea. And we have a full reef or deep water little basin on this side, basin on the other side, a reef, slightly deeper reef sand apron that passes into a lagoon, then another reef flat, so reef sand apron complex on the other side before we go into the other full reef. The model domain was about 3 kilometers by about 5.65 kilometers. So it's just a little more over 4 kilometer, quote unquote, atoll. Now, in terms of what we put into the model, it's driven by waves and tides. The tides we model over a full tidal cycle, but here we'll focus on the spring tides because basically that's where most of the action occurred. For the tides, we actually wanted to see what the impact of tidal range and tidal period was. So we actually used a number of different tidal approximations, including from Malpighi, which is French Polynesia. There, the spring tidal range is about 0.2 of a meter. Bahamas, Aranuka, which is in Kiribati, and Heron Island, which you all know a little bit about, I think, where tidal range is about 3 meters. These are all semi-diurnal tides. We also had Alacran, which is a diurnal tide that's shown in the black here, tidal range of about 0.7 meters. So again, these are all different inputs, different models. We want to see what was the impact of different tidal range and tidal period. I won't focus here on tidal period, but we'll look at different tidal range and impact that has. We had no wind in these models, again, overly simplistic models. And the waves were unidirectional. They all came from the east. And we had a number of different wave height scenarios, 0 meters, 1 meter, 3 meters, and 5 meters in periods of 8, 12, 12 seconds, and 12 seconds. So let's take a look at kind of how the model worked, what we got for output. First thing we'll show, this is the tide. So tides going up and down. These are the Bahamas tides, so just 1 meter tidal range, spring tidal range. What I'll show you in just a second is horizontal particle velocities as a series of curves. These curves have colors, and these colors correspond to different points on the reef sand apron, kind of schematically shown up here in the top. So the warmer colors represent stuff closer to the margin, and the cooler colors represent things towards the lagoon. So if we look at the horizontal particle velocity, which is the Mike 21 a representation of orbital velocities as they become more shear stresses on the bottom. And here, this shows two things. First of all, you note the changes with the tides. So the horizontal particle velocity varies with the tides. And also it varies distance with distance from the margin. Not surprising, the horizontal particle velocities, the waves are strongest right near the margin. They decrease or they're dampened into the platform interior. That's not necessarily too surprising. Let's move on and see what else we can find. Here's the same time plot, again, same colored scheme. Here we're looking at the U component of velocity. So to the right, to the left. Again, you can see that velocity increases with the tides and towards the platform margin. But basically the tides go on the off the platform, then on the platform, and then off the platform. We can also vary the waves, and here we're going to change how we're looking at these systems. We'll look at just one specific point, just right behind the reef. And again, the reef is just about 0.5 meter higher, I should have mentioned. The reef is just about 0.5 meter higher. And again, tides are going up and down. We'll look at 3 waves. First of all, with no waves, so it's just a purely tidal signal, that's the black. Again, you see relatively weak bed shear stress. Less than 1. Same thing with 1 meter waves, so kind of calmer conditions. And then as we increase our wave height to 3 meters and 5 meters, see we get more differentiation. There's a marked increase in bed shear stress. Bed shear stress is up to about 3.2, as I recall, with the largest high tide during this spring tidal range we're looking at. So we can also consider and isolate the influence of tides. As I said, we use different tides in this scenario. Again, we'll look at the same data point. We use just 1 meter waves. Just for comparison with no tides, bed shear stress is about 0.02 Newton meters squared. So we look at this, what you'll see here is, again, Malpedie is a low tidal range, Heron Island is a high end member tidal range. You can see that while the periods are, the times are slightly different, but basically Heron Island has rather large velocities onto the platform and off the platform, onto the platform, off the platform. Malpedie, which is 0.2 meters tidal range, is relatively weak tidal currents. And Bahamas and Aranuka fall in between there. And so we can also try and quantify the influence that tides have. And so basically what we'll do is we'll look at the maximum bed shear stress for each of these during this time interval. The maximum bed shear stress, will plot that against the tidal range. And that's what this plot shows. This is just for 1 point with 1 meter waves. So it's, again, just looking kind of just one variable. This plot shows spring tidal range against maximum bed shear stress. What you can see is, well, there's a relationship. As we increase the spring tidal range, we markedly increase the bed shear stress. And I modeled this, I just stuck a line in here, but in hindsight, it might be more of a nonlinear. Trying to be interesting to look at something about 4 meters, see if it continues up like that, if it is in fact a more linear trend. So tides are of marked influence. Now, those of you who work in the Great Barrier Reef, you know that, but sometimes you read the papers of people who work in French Polynesia and they don't even seem to consider tides as relevant at all. And they're not very relevant. Places like Bahamas and Aranuka in between, they're moderately relevant. So to kind of get to the punchline here, we're just kind of walking through the difference of the influences of different variables. Let's consider the width of the reef sand apron and what influence that might have. And to do that, we'll look at the largest scenario that I considered, 5 waves of 5 meter significant wave height. We'll keep the leeward reef sand apron width constant. All we'll do is vary the width of the waveward reef sand apron in 500 meter increments. So basically, it'll go from something that looks like this, which is kind of everything we've looked at so far, and we'll basically widen till we have a completely filled lagoon. We're going to look at just this 1 point again. And here's our data. Plotted here is bed shear stress versus time. This is from the waveward or eastern margin. Remember, all the waves are coming here from the right-hand side. And what you'll see is, well, not like we've seen before, the bed shear stress varies with the tides. But interestingly, as the reef sand apron goes from 500 meters to enveloping the entire platform, the entire atoll, the bed shear stress decreases. So there's no change in tides, no change in waves, but the bed shear stress changes simply as a function of the geomorphology. This was interesting, at least it's interesting to me as a geologist. I hadn't quite thought of it like this before. But even more interesting to me, again, and y'all smarter than I am, so you might have seen this as well, but if we look at something on the patterns on the leeward margin, and here you see the same tide pattern, obviously slightly different phases, but as we start from a narrow reef sand apron to a broader and completely fill the platform, basically bed shear stress decreases. Decreases actually more markedly on this leeward margin, the other side of the platform, than here on this eastern waveward margin. Again, that was surprising to me. I thought that was interesting. So let's take a look now. These are the big waves, large storm waves. Let's look at kind of what might be a more normal scenario. Let's consider this extra wide, 2,500 meter wide reef sand apron. Here's a bathymetric profile with 1 meter waves. And let's look at what happens as we vary the tides. So tides, different tidal amplitudes. Again, Malpiti is about 20 centimeters, Bahamas a meter, Heron Islands about 3 meters, 2.9 meters, I think, in the scenario that I modeled. And during rising tide, what you see here is that, again, not surprisingly, with low tidal range, there's relatively low bed shear stress. With increasing tidal range, bed shear stress increases. It's also interesting that remember, we have waves coming this side, 1 meter waves. So that with rising tides, water's coming onto the platform. There's actually a point where there's a crossover. And here on the lagoonward flank of the reef sand apron, we actually get eastward flow. It's actually a zone of flow convergence, kind of in the middle of the reef sand apron. And then again, the strong tides coming onto the platform this side. So that was, again, that was maybe, I wasn't necessarily expecting to see that. I was surprised by a lot of this stuff, but that shows how bright I am. Okay, so let's kind of look at this a bit more graphically. We started with a scenario in which we have a 500 meter wide reef sand apron. This is a plot of bed shear stress. The warmer color, the reds and the oranges and the yellows are strong on platform on this side. The purples and pinks are strong on platform on this side. Waves coming from the east, high bed shear stress all across the reef sand apron. When it's this narrow, we broaden it. We start to see a more pronounced decrease across this broader reef sand apron. And these large waves, maybe storm waves, come from this side. As we go to 2,500 meters, you see we actually start to get some markedly decrease. So it's most pronounced on this side, but the bed shear stress, decreases across the reef sand apron. And also, if we pick any one point in space, there's a decrease in bed shear stress through time, or at least with progressive widening. We can look at this slightly differently in a bit more different graphic. This plot shows a transect across the model, the center part of the model. This plot shows bed shear stress of different reef sand apron widths. So all we're doing is varying the width of the reef sand apron on this side. This is during kind of the last gasp of high tide. Tide was actually just coming in just a little bit. Again, you see the same thing with the narrow reef sand apron. We have the highest bed shear stress. And with each progressive widening, at any one point, we get progressively decreasing bed shear stress. So it's kind of an envelope which basically decreases like that. The leeward margin is kind of more or less the same trend, decreasing, but it's not obviously high as this side, because we have waves and incoming tides adding together here. Here the wave-driven currents pushing across this side are counteracting the on-platform currents during, again, the last stages of rising high tide. Now, we can also see what happens during falling tide. And these are just 1 meter tidal range. Here we see the same pattern that in each, with each 500 meter increase in width, we decrease the bed shear stress. There's an interesting trend basically that increases towards the reef, towards the lagoon. We see the strongest bed shear stresses are actually over here on the leeward margin. So being a geologist, I had to come up with an arm-wavy kind of cartoon-like conceptual model to let people hack at it. Basically, conceptual model would be that if we have a platform which is flooded, and it might have marginal reefs, might be flat top, that's kind of what this dash line is supposed to represent, but waves from the eastern side, like an aggradation, the reefs will initiate on the margins, so they'll grow the fastest. So we set up this kind of raised rim. With this narrow reef and reef sand apron, we get elevated bed shear stress with sediment transport to the lagoon. We'll get the expansion of the reef sand apron. As the reef sand apron widens, basically the bed shear stress will decrease, so the carrying capacity will decrease, so we'll get a gradual on-platform fining. Finally, we'll come to some point where the bed shear stress will be insufficient to carry the sediment in the system. That will lead to a decrease in the rate of reef sand apron widening, might even stall the reef sand apron widening. And at this point, we could potentially get island nucleation. And then we might come to some point where the reef sand apron, expansion actually ceases because the bed shear stress is ineffective for transport across the reef sand apron. So this basically suggests, as a conceptual model suggests, that there are negative feedbacks. That is, the very process of widening by sediment transport creates conditions that disfavor further widening. So that would suggest that we limit the possibility of filling platforms and atolls by debris derived from the reef. Of course, as with any study like this, there are a number of limitations. I'll just lay a few out here. I'm sure you all have a few others you can think of. But these are just simple models of empty buckets. There are size effects. I put the asterisk after the will not fill because this one, there is a size effect. Small atolls will fill. They're not simply not large enough that the reef sand can expand enough to decrease the bed shear stress to zero beyond that critical point. The small atolls probably will fill, so they can and will fill. Now, how small is small? I don't know the answer to that question, but that'd be an interesting question for someone to address. There's also 3D effects. We need a simple, basically a numerical flume model. And there are 3D effects. Waves come from different directions, currents coming in and out of the plane. But hopefully, these results encourage additional testing, either in the field, ideally in the field, and also with other simulation models. So I actually had a lot of consideration when I went for the title. I said, are these half full or half empty? Well, we don't have all the, we don't have all the facts, but like this lawsuit against Kentucky Fried Chicken, they got sued. Apparently someone said the bucket was not full enough and that it was advertised as full, but we don't know if it's half full or half empty, but we at least have some facts now. We do have plausible deniability that atolls may not in fact fill given normal processes continuing. So with that, I want to shift gears, hopefully don't grind the gears too much, kind of come to our second conceptual model the geologists love. This is related to the wave-dominated coast, and those of you who study Siliciclastic systems know that they've been subdivided into river-dominated, tide-dominated, wave-dominated systems. We'll consider, again, in our simple world, over-idealized world, the very tip of the apex of the triangle here, wave-dominated, wave-exclusive coasts. We won't have to worry about any kind of river processes or tide processes in this next model. So we'll look at just a pure end member. And implicit in discussions of wave-dominated coasts is the notion of wave base, at least in the geological parameter. And wave base has been variously defined. It's been originally defined by Gulliver, a guy who traveled a lot. He said it's the depth to which maximum wave energy is possible. A maximum, that's kind of a maximum wave action, is kind of a vague term. Nevin Fenneman, I love Nevin Fenneman, that's a great name. But Nevin Fenneman said it's the depth to which wave action ceases to stir the sediment. So Fenneman was actually a stratigrapher. So he said it's important to think about sediments in this system as well. And then John Rich, not big and rich John Rich, but maybe a distant relative. He was a geologist. He said, what's the greatest depth to which the bottom is stirred by waves during storms? And John Rich did a step. He added in addition to sedimentary implications, he said it has geomorphic significance. He was actually the gentleman who came up with the notion of cliniforms. That's where the term cliniform came from, was from his 1951 paper. He said he defined the undothem as the top set, the clinothem as a sloping part of the bed, and the fondothem as the bottom. He said the undothem, unda being Latin for wave, undothem was driven by, see here, depth of wave base. So I thought this whole cliniform models was related to wave action. Now, those of you who are more kind of classic marine scientists opposed to geologists, you'll say, well, hydrodynamic wave base, that's just the water depth at which movement due to the passage of a wave approaches zero or is zero. And this is simply the wavelength divided by 2, half the wavelength, right? It's hydrodynamic wave base. But if you're a geologist, this is irrelevant because you have to see evidence for sediment disruption. There has to be something happen on the seafloor for it to be preserved in the rock record. So geologists have been moving towards using what's known as effective wave base. That's the depth above which wave orbital velocities in the bed exceed the threshold for initiation of movement of sediment. So effective wave base is a function of wave energy, but then there's other things. It's really this other things I want to spend the rest of our time talking about. Again, my focus as a geologist is focus on the geological aspects of this, because effective wave base is what we see in the rock record. That I start here somewhat facetiously saying, is wave base, does it actually exist? Well, if you read the literature, and hopefully you can see this, I know these are all kind of small, details in these don't matter, except to say there's just going to be a series of profiles. This is from Gary Hampson paper. So here you see storm wave base and fair weather wave base, fair weather wave base, storm wave base, fair weather wave base, storm wave base. These are all Siliciclastic systems. James Lee Wilson, his classic 1975 textbook on carbonates, said, well, the facies differentiation, storm wave base, fair weather wave base, fair weather storm, fair weather storm, fair weather storm, fair weather storm. Oh, this guy actually put some numbers on it. So while being real gutsy, fair weather storm wave base. You get the point. Fair weather storm, fair weather storm, fair weather storm, fair weather storm, fair weather storm. So these, of course, some folks, even Noel James, they have, so this is Adrian Immenhauser's stuff after Noel James. There's hydrodynamic wave base, hydrodynamic swell wave base, hydrodynamic storm wave base. So all kind of different, there's wave base for every occasion, as they say. Again, as a geologist look at this, we commonly encounter things, and it's based on observations like this. Go to the outcrop. This is from the book cliffs, as I recall. See, a succession looks like this. If you go up and look at the rocks in detail, what you see is that the lower part, these are from 5 to more than 20 meters thick. Lower part is bioturbated mud, which is interpreted to be very low energy. This succession gradually coarsens up. In the lower part, the wave ripples. These pass upward into thicker bedded, slightly coarser, hummocky cross stratification. So these are all wave generated sedimentary structures. These pass up into trough cross stratification and current ripples. And these are current generated sedimentary structures that are most commonly interpreted to represent persistent agitation. And these kind of observations and interpretations have been, oh, the computer's freezing. Sorry, my computer froze. Yep. My computer froze. Can you hear me?
Yes, we
Yeah,
can
we can
hear
hear
you.
Okay, sorry, I'll PowerPoint froze on me. I'm trying to recover. Okay. Okay. Let's see. Let me open it back up again. Apologies for that.
That's okay. It happens.
Okay, let's see, where was I? Oh, okay, let me share my screen. Okay, can you see that?
Yes, we can.
Yeah, good.
Okay, good. Thank you. Okay, so we're talking about succession, and folks, geologists have interpreted these to represent environments such as offshore, lower shore face, upper shore face, and foreshore, basically your beach deposits up here at the top. And from this, they draw interpretations about wave base. Oh, it's freezing. Okay, interpretations of wave base. So storm wave base down here, which is basically the deepest or the first occurrence of evidence for wave activity. Fair weather wave base, where you go from hummocks to troughs. But other authors say, well, they interpret a little bit differently. Here's a lower offshore, upper offshore, lower shore face is up here, middle shore face, upper shore face, and foreshore. And they say, well, no, actually, storm wave base is down here and fair weather wave base is here. So there's a divergence of not only nomenclature for what the rocks represent, but actually the processes behind the deposition of these different sedimentary structures. And it becomes even more complicated when you realize that, well, all these are not the same thickness. There's some which are much thinner and some which are much thicker. So it hasn't stopped folks. If you look at any sedimentologic and stratigraphic textbook, you'll see things which look like this. For Siliciclastic shelves, here's a homoclinally dipping shelf, storm wave base, fair weather wave base, and the stratigraphic interpretation of those, kind of like we saw on the last slide. This is true for Siliciclastic shelves, but the carbonated folks not wanting to be outdone have said, well, we can do that too. If things which are deposited below storm wave base, which would be muddy deposits, maybe outer ramp, middle ramp between storm wave base and fair weather wave base, and above wave base is inner ramp of the persistently agitated stuff. So the storm wave base is kind of the deepest occurrence or evidence for wave action. These paradigms are in both carbonate and siliciclastic systems. And point is, they emphasize the role of waves and wave agitation. So now, this is all academic crap, right? Who cares about this stuff? Well, why do we care about this stuff? Or why should you care about this? Well, wave base, again, is the foundation for many conceptual facies models of both carbonates and siliciclastics. It's also used to derive other interpretations, everything from water depths. People try to quantify water depths, ecological zonation conditions, regional stratigraphic correlations, even eustatic changes in sea level have been derived based on interpretations of wave base. So, but does it make physical sense? Let's take a look at that. That's the second part of the talk we'll discuss. Again, we use Mike 21 again, and basically doing a similar numerical flume experiment. Here's our model. I think this is a kilometer wide and varying widths. A kilometer too wide, I think I varied it. The dip varied. We'll have different dip angles, different bathymetric scenarios. We'll look at sigmoids and homoclines, so gently dipping ramps or steeply dipping ramps. And it'll be forced by waves normal to the shoreline. So again, like the last one, waves will just be from the east, from unidirectional waves. So as such, there's no longshore currents. Like I said, we're looking at the pure wave-dominated end member. I don't think it gets any easier once you start introducing currents or tides or stuff like that. So let's start, I said, let's just start with the simplest model we could. So there's no currents, no regional currents, no tides, anything like that. We had a 6-hour time step. We simulated 1 year. Now I'll show you data that represent extractions from this kind of the center of the model. We'll look at this, how this varies through time. This will be the strip that we'll look at right through the center of the model. And we'll look at scenarios that mimic a homoclinal ramps. This is gently dipping from 0 meters to 200 meters. Again, waves will be from the left side to the right exclusively. We'll also consider a homoclinal ramp. One that starts at 0 meters water depth up here, another that starts at 5 meters. So we'll kind of shift the ramp up and down basically. The waves that we use as input in the data come from just north of the Bahamas, so kind of offshore Florida. And here's a time series. This is from February to February. So this is our Northern Hemisphere winter. You see the higher waves, and red is significant wave height, blue is wave period. See the larger waves in the winter, kind of decrease in the summer, larger waves again in the winter. See this, again, quiet summer, but you notice these two blips, these are hurricanes, and this is actually Hurricane Dorian, which is a category 5. When it moved through the area, it did one of the largest hurricanes, worst hurricanes hit the Bahamas in years and years. So we'll take a look at what that does to the scenario. And at this point, I said, well, there's clearly seasonal changes. There's days with bigger waves and days with smaller waves. But it reminded me of the question, how big is a big dog, right? How big is a storm wave? How big is a fair weather wave? And everyone would agree that that's a big dog. That's a really big dog. But is that a big dog? Well, if that dog is on your couch between you and the remote control, or you and your beer, and it's growling at you, making that face, and that's a big dog. So it kind of becomes relative. But so I guess the question we want to ask here is there how big is the impact of a storm weather wave or a fair weather wave? And is there a bimodal distribution? Like I said, all those cross sections I showed you, the schematic conceptual models had, well, here's fair weather wave base and here's storm wave base. Those are definitive positions, and we can define those, this and the other thing. So here's start of our data. And this plot shows for that transect goes from shallow water to deep water. And this is basically a time series from February to February. It's a time series of orbital velocities. So the warmer colors represent higher orbital velocities. See shallower water, higher orbital velocities. Deeper water, black is 0 or no data. so lower orbital velocities. And you can see that there's some rather extreme orbital velocities, especially right here. This is Hurricane Dorian. So this model predicts that had Hurricane Dorian hit this idealized ramp, water would have been moving at the bottom, even at 200 meters water depth. Now this is for a steep ramp. This is 20 kilometers across, so 0 to 200 meters water depth across 20 kilometers. It's about a little over half a degree. We could say, look at the same data. So here now, let's plot this draped on time, or sorry, not time, draped on depth. So again, here's our shallow to deep. Here's our February through time, Hurricane Dorian to February. Velocity is slightly different, again, different color scale. This is our steep profile. Let's look at it. What happens if we have the same waves, we impart a shallow profile. This is about a little more than half, at about a quarter of a degree. You'll note up here where you see all these reds popping in. Down here, there's basically no reds. There's actually some here, but just too small. You might not be able to see them. I can't see them on my screen, but I know they're there. So they have similar patterns. You see, well, kind of winter, summer, winter, Hurricane Dorian, winter. Same type patterns, but the numbers, the details are distinct, and specifically the steeper profile has higher velocities. I'd also ask you to say, I challenge someone to say, identify for me, where is Fairweather wave basin here? There's kind of a, it looks like a complete spectrum. We'll come back to that point in just a second. Let's look at this a little bit differently. What if we have a sigmoidal profile? Here we just go to 0 to 100 meters. And so this, we start at shallowest water, and we see a decrease as we get up to the shallow, the wave break, dissipate their energy right in here. So we look, we shift it down 5 meters, so now the shallowest part of the sigmoid is in 5 meters water depth. See, we still decrease velocities onto the, or up ramp or up sigmoid, but we still get velocities here. There's a velocity decrease. Peak velocities are kind of in this area near the top side of the ramp, but the details, again, the absolute values differ markedly. And again, I'd say, where is Fairweather wave base? These are the same waves. We can look at this question a bit more rigorously, perhaps, and say, let's look at these and sum them, look at this probabilistically. This is the same plot we saw before, from shallow to deep through time. What we do is basically take every bin, every 5 meter bin, and summarize it in terms of a probability distribution. So this plot shows probability in the colors versus water depth versus horizontal particle velocity. So it's horizontal particle velocity versus water depth with the probabilities marked. So the way you'd read this would be, at 50 meters water depth, there's a 1%, so this light blue, 1% probability of exceeding 60 centimeters per second. In contrast, at 10 meters water depth, there's a 100% probability of exceeding 60 centimeters per second. So basically we're right in this kind of sweet spot right here. We're always over 60 centimeters per second. So now what we'll do is we'll take this plot, we'll rotate it 90 degrees so that we have depth on the y-axis and horizontal particle velocity on the x-axis. This is, again, we looked at just before, and here's our steep ramp. Now here's our shallow ramp. It's just a few things to point out here. First of all, these are the same waves, exact same waves, relatively subtle. We could envision a lot greater change in gradient. So relatively subtle, let's say, change in gradient, change in maxima, distinct maxima, about 1.5 to about 1 meter per second in this example. Likewise, we might consider, we said Fairweather wave bases areas with persistent agitation at 10 meters water depth. In this one, we exceed 60 centimeters per second 100% of the time. On the gentle ramp, we exceed at 10 meters water depth 100% of the time, we only exceed 25 centimeters per second. So it's a marked difference. And is this bimodal? Do we see a distinct storm wave base and Fairweather wave base? No, rather it's a continuum. It's not a distinct bimodal distribution. So maybe we're looking at this wrong. And McCabe published a paper. We suggested that if we consider the work, look at it differently related to work. He said, we want to consider the maximum geomorphic and sedimentological work. And he said that will occur where the rate of sediment movement times the frequency of occurrence is at a maximum. And so sediment transport rate is proportional to fluid power. Fluid power is proportional to the cube of peak orbital velocity, peak orbital speed. And so the way he suggests a wave effectiveness parameter, which is just the cube of peak orbital speed times the exceedance probability of that speed. Okay, so that's what we'll look at. We'll look at these plotted by depth. If we take this wave effective parameter, add it up for each depth, so all probability speed cubed by depth, you'll see there's different, each of these is unimodal, but they're distinct and they're different by, depending on whether you're on the gentle homocline, steep homocline, sigmoid, shallow sigmoid, or deep sigmoid. If we zoom in and look at this a little closer, you see that the peaks and the magnitudes of the total are very different. So that suggests that the low energy ramp would be very different from, sorry, the gentle ramp would be very different from the steep ramp. The two homoclines, which same profiles, but starting at different points, are different as well. These are the same waves. Again, as geologists, we don't know, we never know what the waves are. We have no clue what the waves are. We can also consider, rather than considering total work, we can consider the conditions with the most work, and that's for the maximum wave effectiveness parameter at each depth. And these are created by waves with some orbital velocity. And if we consider that orbital velocity, so this is a velocity at maximum wave effectiveness parameter, again, we see there are differences. And again, these are forced by the same waves. Most have a peak at about 10 to 20 meters water depth. Steeper profiles have higher velocities. We can also think in terms of sedimentary structures which are produced. There was a paper back in 2006 by Dumas and Arnott, and they suggested that HCS, hummocky cross-stratification, occurred where currents were less than 10 centimeters per second, but orbital velocities were greater than 50 centimeters per second. So where would these occur? Well, on the shallow sigmoid might occur at about 50 meters water depth. It wouldn't occur, would not be exceeded until about 25 meters water depth in this gentle homoclinal ramp. So again, these are the same waves, very different energy imparted on the seafloor. So let's go back to the question, where is fair weather wave base? Where is storm wave base? I'd argue that they're figments of your imagination. Fair weather wave base is. Storm wave base, well, you can pick out some point where the orbital velocity is sufficient to disrupt sediment and generate sedimentary structures, but that also depends on the sediment. If we're in carbonate world, like I like to stay most of the time, we had various carbonate producing organisms that produce shells of different sizes, densities, shapes, internal porosities, and these will have different transportability. So the sediment movement depends also on the sediment. Again, whether you're in a halometa or skeletal sand, it's covered with vegetation, which we don't even, heaven forbid, we have to think about that, or bivalve shells like in this scenario. These have different susceptibility to transport. And each of these three, these are taken at the same water depth in the modern Yucatan ramp. These have very different susceptibilities to transport given some orbital velocity. So it gets even more complicated if you're in carbonate world. I can't end this seminar saying that, wow, it's all a bunch of crap, because I don't believe it is a bunch of crap. But we can say that there may be some feedbacks in these systems. Even if we have constant waves, if we have steeper gradients, hopefully I've convinced you that these steeper gradients will lead to higher energy. This higher energy could also favor transport of coarser grains. These coarser grains, what do they do? Well, in fact, feedback, and they will favor the occurrence of steeper gradients. So maybe there are these morphodynamic feedbacks in ramp systems. Again, I'm by training a geologist and stratigrapher, and so I want to consider some of the implications of these notions. We'll start out by considering a classic depositional profile. This could be anywhere from 10 to 1,000 or more kilometers across, and this could be 5 to 100 or more meters. But the classic sequence stratigraphic interpretation would say, well, in observations of many sequences suggest we start with relatively low gradient profiles. These might be your transgressive systems track, for example. So a little back step here, so some agrades and then progrades, so transgressive early high stand, late high stand. But basically the profile evolves. By this time you start to think, okay, so what if we started with a profile, this blue line here that looks like this, and we might have an effective wave base or transport sediment down to this depth. If we keep the sediment grade constant, so sediment supply is constant, we start with this profile. What happens by the time we get to this last profile? Because I'm in PowerPoint, I can give it the same height. But if we have the same waves, the exact same waves impacting this profile and this profile, hopefully I've showed you, I've convinced you that, well, we might actually get a thicker sand body because the effective wave base is actually deeper. Now, in carbonate world, we may or may not assume that sediment grade is constant, but we actually may get variable sediment grade. We might start out with a skeletal mudstone to actually a pack stone, but low energy in these lower part. And what do you think is going to happen as we go over here? Again, same waves, not saying waves are the same, but at least it's plausible they could be the same. Or if there were no change in waves, what would we expect to see? Well, this steeper profile would be higher energy, so it could be more coarse and grainy, but it could have, because it's coarser and grainy, it could have the same wave base, exact same water depth for wave base, effective wave base for sediments transported as this. So again, this is a complicated system. Now, going back to Shaheen Dashgard's paper, great paper, he recognized, he said, well, some of these shoreface successions are shallow, or sorry, thin sands. Others have progressively thicker sands. He said, well, this is clearly a reflection of wave base, fair weather and storm wave base increasing. He said, well, this is all due to, I don't know, my computer's freezing me. These are all due to storms and increased gradients. And so he suggests it's related to storm energy. Is it related to storm energy, or could this be a reflection simply of gradient? Do we know for sure that wave energy, storm energy, in fact, increased or would increase? And one study recently published by Bruce Ainsworth looked at this question about shoreface sands and gradient. He compared the mean sand thickness on shorefaces shelves of various gradients. Low gradient shelves had a sand, discounting things like compaction, stuff like that. This had a sand with a mean thickness of 6.3 meters. And then when you look at shoreface sands, which are steep, greater than about 0.05 degrees, I'll give you one guess. You think these are going to be thinner or thicker sands? You're right, exactly right. These are much thicker sands. So again, does this prove that wave energy was not different? No. But it could be the same wave energy. Again, we don't have independent means to test that, or I like to think of independent means to test that, but it's an assumption that the wave energy is different. It could be different gradients that drive these factors. It's not just in classics, it could occur in carbonates as well. There's a study from Morelli and Pierre a couple years ago, and it looked at cycle from the Jurassic, from the Jurassic, basically transgressive, early high stand, late high stand. And this, and I don't know if you can read this, but basically this says for low slope environment, 0.1 degree, what do you think the rocks in this lower part are like? Well, let's see, muddy ramps. And then in the upper part with the steeper gradients up to 3 and 4 degrees, what do you think these deposits are like? Lo and behold, high energy oolitic ramps, all kind of tempestites, so storm deposits. Now, does this prove that waves are not different? Well, no, of course not, but it's at least, it'd be an assumption to say that they are. Gradient could be just as important as a control. Okay, so to kind of wrap it up, I'll give you a graphic summary because I've been rambling on for a while now, but I would argue that fair weather wave base is a figment of our imagination. So we can cross that one out. Effective wave base is a function of wave energy. It's also a function of the sediment that's available. And in carbonate systems, we need to think about that. It's a function of gradient, not to mention any currents, which can add or modify orbital velocity or initiation of sediment transport. I made the case that a steeper gradient will create a higher energy conditions across a ramp, which can lead to coarser grains, which will feedback lead to steeper gradient. And it's effective, effective wave base in one setting is not the same as effective wave base in another setting. Even with identical waves, wave bases are not directly comparable among shelves, perhaps even within the same shelf through time. That's because, hopefully I've made the case, that hydrodynamics are encoded differently by shelves of different morphology and different sedimentology. So the take-home messages, hopefully you came away with, is that geologists, sedimentologists, and stratigraphers are quite creative. Conceptual models can and should be tested numerically. Hopefully found some interest in these studies that suggest that reef sand inference will not, again, big asterisk there, will not, but I have to be somewhat provocative, will not fill lagoons. And we talked about the wily basis of wave bases and the importance of bathymetric gradients in those. So hopefully you found some. Okay, so with that, I'd be happy to answer any questions. I had one request already for an interpretive dance, but I'm not a good dancer, so you're going to have to imagine me doing that. And if you're looking at the recorded version, feel free to send me an email. There's my email address.